Before starting the discussion on the different implementations of different seismic methods for the subsurface characterization, let's review once again how seismic methods work. Essentially, they are geophysical techniques that are able to provide images of the subsurface, but also to measure the propagation velocity of the seismic waves, the different types of seismic waves, P and S and Rayleigh waves, and estimate the absorption. The absorption is representing the inelastic behavior of soils and is something that might be relevant in some site simulation response. Measuring the velocity essentially requires measuring the distance and the time. And for a given wave type, for example P or S, for a given estimated propagation path, because from the data we might understand that there's a refraction, but we do not know exactly the geometry of the layer which is refracting, we estimate the propagation velocity. So the distance is measured in the field, knowing the position of different receivers at the surface or down into a borehole. And the actual true path of the waves is only indirectly estimated, unless we are using borehole data, where we know that we are following normally the direct propagation path from the source down to receivers. Or when we have two closed boreholes, we imagine that the path is the direct, shortest path between the source and the receiver. But essentially the distance measurement requires some survey effort, at least to know where each of the receivers and where the source is. The time, the second part of the estimation of velocity, is measured analyzing the seismic data, trying to identify the arrival time of different seismic events and trying to identify which type of path we are looking at. Because the apparent velocity that we have in seismic record is to be converted into a true velocity, and we need to do that to know which is the propagation path. So, again, let's review what are the different components that are visible in seismic data. The refraction seismic is probably the most used techniques for shallow applications, essentially because it's easy to deploy. Essentially because on seismic traces, we look for the first arrival travel time. So we try to identify on each trace at what time the first coherent source-generated energy arrives. And the shortest from an optical, from an acoustic seismic path is typically the refracted path between the source and the receiver. So when we have records of traces with a refracted component in the wave field, we can pick the arrival time, we can identify the distance between receivers. You see here in this pair of traces the delta x, and the delta t will be the time difference between the two. But this is not everything in the seismic data. After the first arrivals, there are lots of other useful things. For example, we have reflections. In this shot gather, so a collection of traces for a single shot, you see the direct and refracted arrivals annotated with the blue line on top. The energy that you see before the first arrival is only ambient noise, incoherent noise. And in this particular display, there's a gain, a time variant gain, which is scaling up the energy on a sliding window. And it looks like there's some energy before the first arrivals, parallel to the first arrivals. It is purely an effect of the scaling of this gather. The reflected energy, annotated here with these red hyperbolic lines, is the energy that is sent from the source down into the Earth interior. It's reflected up by some interfaces with a reflectivity. And the reflectivity is related to the difference of impedance across the boundaries. And the impedance is the product of velocity and mass density. So when there's a change of lithology, the energy that is going down is also reflected up, besides continuing its propagation down, curving its path due to the transmission change of direction due to the refraction. Essentially, the reflection has a shape, this hyperbolic shape, that is annotated onto the gather and displayed schematically on the right-hand side with this little half hyperbola. This shape is a function of the geometry, which is a known parameter of the acquisition, the distance between the source and the receivers, but also is a function of the velocity. So the velocity analysis with reflection data is essentially identifying the curvature of this hyperbola to identify what is the average velocity from the surface down to this reflector. But there are other things. And there are, for example, the surface waves. When you look at this example of a single trace, you see how variable can be the property of the seismic energy arriving to a single trace. You see, for example, on the top left, a single trace which is recorded at 20 meters from the source with two different packages of energy. A high frequency arrival, an early arrival, and then a later arrival with much lower frequencies. In the time frequency representation that you have just below this figure, we display on the horizontal axis the travel time, the arrival time, on the vertical axis the frequency. And you see that these two components of the wave field arrive at different time. It means that they have very different velocities, but they also have very different frequency ranges. And these are the surface waves. We are showing here a saturated, water-saturated site with soft sediments. The water saturated is normal. In many cases we have the groundwater with the top of the saturated zone, which can be very close to the surface, especially when we are in plain areas close to rivers, or in any areas in the plain. For example, in northern Italy, often the water table is not very deep. So we get a high velocity associated to the compressional waves and the refracted waves, and then a much slower velocity associated to the shear waves and the surface waves. And what is extremely important for the geotechnical characterization is the behavior of the solid skeleton. We are not really interested in knowing what happens if there is groundwater, because the failure of a site under static or dynamic actions is not happening because of compression failure. In most of the cases it will be shear failure. So the properties that we are interested in are the shear properties. And we are not interested in knowing that in many cases a saturating groundwater is at a certain depth. We are interested in getting the mechanical properties of the solid skeleton, of the matrix of the subsurface solid media. And the shear waves are extremely important for that. This is why for the site characterization and for many geotechnical problems, shear waves is the way to go. So we talked about P and S waves, shear waves, but in practice we will see animations later. These are very common and used cartoons showing the P waves, the compressional waves, propagating in a certain direction with a particle motion parallel to the direction of propagation and inducing essentially compression into the material that they go through. The shear waves have a particle motion which is perpendicular to the direction of propagation, and essentially they induce a shear, which means that the shape of the element is changing and its volume is not. And this is one of the reasons you can imagine that if the volume is not changing, the compressibility of the object is not affected, and the saturating fluids have a much lower importance. The surface waves, and in particular the Rayleigh waves, exist only when there is a free surface, the boundary between the solid medium and a medium in which shear waves do not propagate. It could be the vacuum, or it could be just the atmosphere with zero shear wave velocity and a much lower mass density. And the surface waves are a very important component of the wave field because they are easy to acquire and they provide us velocities which are very directly related to the shear wave velocity. This is why there will be a specific module in this course on surface waves. So the body waves and surface waves have a fundamentally different behavior. The body waves propagate down into the Earth interior. When we have a source down at depth, for example, a deep explosion, a nuclear test for someone that is not respecting the nuclear ban treaties, or an earthquake, this energy will propagate in all directions on a spherical wavefront. If we have the source at the surface, the wavefront will be, let's say, half of a sphere. The wavefront will increase with the square of the distance, and the energy will spread over a surface which is increasing with the square of the distance. So the geometrical spreading will be related to the square of r, the distance from the source. And the surface wave will stay close to the surface. They will propagate parallel to the surface. Once they are completely developed at a certain distance out of the near field, the wavefront will be cylindrical. Their surface will increase with the distance, and we'll have these cylindrical wavefronts with an energy decreasing with r and an amplitude therefore decreasing with the square root of r. It means that with surface sources, we typically have very strong surface waves into the near field.